Hey, Jen, how you going? Very tired as well here. Just trying to find which questions we're going over today.
I see.
Hello?
Why?
I want to go through one of the questions today, unless I'd find something else. Okay. See, nobody's really uploaded anything yet. I might go over 31 to 36, maybe 40, 44, 48. Okay.
I haven't even opened the book yet.
Yes, but questions 1, 9, 14, and 16 are all covered in videos.
Do we have to hand something in?
Yes. Yes, I will get out of this and I will move it to the top of the thing so that you can see it there. Gosh, it's lost.
Is this our last chapter?
I didn't expect it to be, but it depends on how you answer the question of what you want to do for your final project. I did want to do a little bit on current, but maybe we might not get there. Let's do some work on capacitance. Admit. Might just be the three of us today. Nope. Okay. Might just be the four of us today. Okay. So for part of your project, you have to describe in terms of. Don't blow away. You're sitting near an open door and everything's blowing in. Okay. So, let's share screen and get a whiteboard going. Okay. Alrighty then. So let's start with question 31 on page 490. Okay. Everybody say hi, Aiden and Ethan. Hi, Aiden and Ethan. There you go. Okay. The two plates of a capacitor hold 2,500 microcoulomb. Why didn't they just say 2.5 millicoulomb? Seems odd. Well, whatever. I can work with that. They both hold? They both hold a different type of charge. All right, so we'll start with. Okay. Actually, it doesn't even say that they're connected through a circuit. I'm going to say 2.5 millicoulombs because I can actually write millicoulombs. And negative 2.5 millicoulombs. Which direction, if you use your drawing capacity here, can you give me the direction of the field? Which way is the electric field traveling?
Go towards,
Okay. I can barely hear you.
Go.
I can't hear you, Lydia. Your microphone is either very low or you've got it so far down on the thing that you can't hear. I can't hear you, Lydia. That's on purpose. Okay. Just to comment on your thing, Melody. An electric field is always in one particular direction. It goes away from a positive source. So it will always be, yes, that's exactly it. An electric field is always away from the positive. Okay. So we then want to figure out what the capacitance is. Anybody want to have a go at that? Top to bottom, not up to down. Up is a direction, down is a direction, top to bottom. So in this case, the electric field would be down. Oh, no. Because you can't go, if you're heading up and I'm heading top, it's a different thing. Up is a direction. Top is a place. Just the same way bottom is a place and down is a direction. Okay. Oh goodness, I sometimes wonder who I'm related to. All right. Okay, so can we have a go at actually trying to answer this question? What is the capacitance? Give you a hint. It says section 17.7. This should be very easy just to stick it into a formula of if you stuck it into that formula from page 480. Let me see if I can edit this. Why can't I edit you? There you go. Can you tell me what the capacitance is? You can type it anytime you want on
The
Sorry?
capacitance is just what's it? The voltage times the what's it called? Sorry.
It's the charge divided by the voltage.
But you put here Q equals CV.
Yes, so C is the capacitance, Q is the charge, and V is the voltage.
Oh, sorry, I was reading that wrong. Yes, charge is equal to capacitance. Okay.
Have we got any solution to this? Can you actually put it up on the text on the screen? 2.9 times 10 to the negative 6. So your value Q here, if you put it into just C, would be Q is equal to 2.5 times 10 to the negative 3 coulombs. So it should be in that order of magnitude. You're not multiplying the amount of charge together.
It's just that times the 850 volts, right?
Are you sure?
No. That divided by the 850 volts. Oh goodness.
The only thing that I have a bit of a question about is I'm a bit unsure if there was the top plate that was at 2.5 millicoulombs and the bottom plate was at 0 coulombs. The only thing that was moving was the one set of charge. I get it, but I don't see which one is moving. Is it one set of charge that moves, or is it both? And does it make a difference? So here's my question. Do you have to add this value to this value? Do they need to be added together, or do you just look at the one that moves?
How do we know?
That's what I'm asking you. I actually don't know. So let's go to the example on page 481. We don't need the area on distance. Do you have, if you know the charge, do you need to have to figure out the rest of it? This is most confusing.
What number is this? What like problem?
Oh, this is problem 31, page 490. And I think I've got the answer at the bottom of page 480. So at the bottom of page 480, and I'll read this out. So it's got that picture at the bottom of page 480. I'll hold it up so you can see what I'm talking about. So there's that picture there. Can you see that there is a Q and a Q plus? Please acknowledge that you've seen the Q and the Q plus. Okay, you got that? All right. So if there's both Q and Q plus in that capacitor arrangement, and they're only talking about a Q, that means you only want to look at one of them. And maybe this has to do with both sides of this capacitor will be at the same charge, equal and opposite. Maybe. I'm actually kind of unsure about this. Do they always have an equal and opposite charge? Maybe they have to have an equal and opposite charge. All right, let's have a look at the bottom of page 480. If a voltage is applied across a capacitor by connecting the capacitor to a battery with the conducting wires, the two plates quickly become charged. One plate acquires a negative charge and the other equal amount. An equal amount of positive charge. Each battery terminal and the plate with the capacitor connected to it are the same potential. Hence, the full battery voltage appears across the capacitor for a given capacitor found the amount of charge Q acquired by each plate is proportional to the magnitude of the potential difference between them. Okay, so you're only looking at one of the Q charges. So it actually, you don't need to add them together at all. You just take one of them. This is kind of a trick question, number 31, because all you need to do is look at the charge of one of the sides. And you just need to know the magnitude of that.
How do we know which side to look at if they're different charges? Or are they always going to be the same?
That's what it said here. One plate acquires a negative charge, the other an equal amount of positive charge. Bottom of page 480. So apparently they're supposed to have an equal and opposite charge all the time. And for the purpose of this equation, you only need to look at one of them. Okay, that bit I did not quite get. So we just plug that into the formula now. That was the only thing that I was really concerned about because I didn't quite understand it. So we can then manipulate this to find the capacitance as equal to the charge divided by the voltage, which should be 2.5, actually 0.0025 divided by 850. I think Weston's going to get a closer number to it. Yeah, 2.94 times 10 to the negative 6. Very good. That's the correct answer. Who put that up there? Who put 2.94 times 10 to the negative 6 up there?
Weston did.
Good on you, Weston. Well done. Unless you took it from the person who put it in your book before you. In which case, well done. And I can edit what you've written. Great. All right, moving on. We'll go to question 36. Yes, using your resources to your full advantage. Thank you. All right, let's move on to question 31. 31. Question 36, same page. The charge on a capacitor increases by 18 microcoulombs when the voltage across it increases from 97 volts to 121. What is the capacitance of the capacitor? Ooh. Ooh, that's interesting. I want to start.
Which question is this?
Question 36. So this is the question, Yejin. So we have our change in, we have a Q1. I wonder if there has to be a change in there. That's Q2 equals Q1 plus 18 microcoulombs. Voltage 2 equals 121. Voltage 1 equals 97 volts. Interesting. Okay. C equals question mark. Okay, so this is going to be a simultaneous equation just because your capacitance of your capacitor does not change. It stays the same. So your rating of your capacitor will stay the same. So what you basically have is C1 equals your charge 1 divided by voltage 1. And C2 equals charge 2 divided by voltage 2. You can then rearrange that to be just equal that. And we have V1 and V2, and we have Q1 in terms of Q2. Oh, I hate these questions. The first voltage is 97. Q1 plus 18. So not 18. 1.8 times 10 to the negative 5. Divided by, does that look about right? Does that look about right? I don't know what thumb on the chin means. That means good?
I don't think that's right.
Why not? What can I do instead?
Isn't it supposed to be 1.8 times 10 to the negative 12 divided by 121 volts minus 97 volts?
What do you mean 10 to the negative 12? How'd you get 10 to the negative 12?
Because it's 18. UC. I don't know how to read that.
Yeah, microcoulombs. That's 10 to the negative 6. MC is, sorry, the mu. That's, which symbol is it? This symbol?
Mm-hmm.
That is equal to 10 to the negative 6C. Does that make sense?
Yeah.
Okay. So if this is already, if the 18 there, I'm just taking the comma point there.
Oh, okay, I see. So it's 1 point, then, wait.
Okay, so we want to try to get all the unknowns on one side. Let's try to get all the unknowns on one side here. So if we get all the unknowns on one side,
There.
you have Q1. We have that there. Then we have 97 divided by 121. That doesn't help me a lot. Can I get a value for? So you're saying, Viajin, that this is then the answer for Q1?
Isn't that 7.5 times 10 to the negative 7 the answer?
I have not gone through this.
저 수업하는 중이야.
Well, there's no squares or anything unusual like that. So it should just be a straight line relationship. So 97 goes up by 24.
And the symbol
should come up with something fairly nice and easy to do.
Did mine get erased?
Sorry?
No, nothing.
Okay, 0.8. This whole hoo-ha again. 0.8. Roughly 0.8. Let's put it back in the other spot and then multiply it through.
What does your answer book say?
I have no idea. I didn't bring the answer book home with me.
Is there even an answer book? I thought you said there wasn't.
There's an answer book at school, but not really.
What does that mean?
It doesn't give every single answer.
Andrew, I don't think my answer goes for Q1.
I'm not sure if I'm even doing it the correct
My
way.
answer is for the...
For the what?
Are we looking for C1 or C2?
C1 will equal C2. Your capacitance will be the same.
All right.
And hence why I'm not very good with these multiple equations at the same time. I'm probably going a bit overboard here. So if anybody can help me with better math than me, that'd probably be helpful. This doesn't look very elegant.
Do you have to end up using the quadratic formula?
No, because I know in my head that this value here is roughly 1/5. So if you times that by 5, you'll get close to the answer. Just
Andrew?
because I know that if this is 80%, if this is 80% the charge of Q1, adding this, that means that this must be equal to. So if I have that as 4 and 5, I guess I can do it as this. So this is 4 on 5, and I have. It's the same as that means that 1.44 will be equal to 1/5. Does that make sense? Does that make sense what I'm doing here? If 0.8 Q1 plus the other thing that you need to add to do is be 0.2 Q1. So this has to equal to 0.2 Q1. Oh, goodness, sorry. I am so dumb. Duh. 1 minus 0.8 Q1 equals that. That's what I'm doing. Okay. So 0.2 Q1 equals that. So it's 1.44 divided by 0.2. 1.44. $7.2. And then I plug that value back into the equation up here. Hey, not far off. So no Q.
The answer was the answer.
Sorry?
The answer was the answer for C. Okay, never mind. Yeah, just. Yeah.
There's my voltage for 197. What does that get me? What should that get me? If you know that 97 is close to 100, you'd be looking at what? If you divide it by roughly 100, what would your answer be?
It's like Yejin's right. 7 point. I guess you have 7.2 times 10 to the negative 7.
Yejin was right. 7.4 times 10 to the negative 7. That's absolutely correct. But if you were to just give me that, and I don't have this as how you're working it out. Yep.
I think that's like way too complicated steps then.
How did you do it?
Because I thought it's simple. Because it says the charge on the capacitor increases by 18
Yep.
microcoulomb.
Mm-hmm.
When the voltage across it increases from 97 volts to 221 volts. So they already tell us how much it changes in the capacitor, which is 18 microcoulomb.
Yep.
And voltage change is 121 minus 97, right?
Yeah, so 24.
Yeah. So all you need to do is just do 1.8 times 10 to the negative 5 divided by 24 volts.
Oh, you're kidding!
Wait, so we went through all those steps.
Because it's showing the change, only the change. You don't need to find what it was before and later.
Oh. I just got schooled by one of my students. No, I'm just dumb. Yeah, Jin. I feel like you are at a sore disadvantage having me as a teacher.
Oh no, it's fine.
I do. And on that note, I'm going to say thank you very much for coming to physics class. And I expect some sort of equation. Use a simpler Yejin equation than a more difficult Mr. Hendro equation. And yeah, we'll go through the PowerPoints on Wednesday for the test. Okay. Is there anything you guys would like to say, ask?
Yes. My capacitor, I've tried like 3 different versions and nothing's working. I don't get why.
What do you mean nothing is working?
Like, you know how the whole thing, like the light's supposed to like slowly like flicker down or up or whatever?
Mm-hmm.
It's exactly the same as if the capacitor wasn't there.
Mine's like that too.
At any point,
And the multimeter?
At any point, do the pieces of foil touch each other? Okay, so they're completely separated by the dielectric.
And the multimeter, I don't get it. Like, I'm wondering if the capacitance is like too small or something in my thing, because it doesn't measure anything. Like the multimeter, like, I don't know.
Have you tried to, have you connected it to an application like a light or something? Or a motor?
I did.
What?
You connected yours to a motor? Or to a flashlight
No,
light?
to a light.
Okay, and what happened?
No, it just turns off like instantly. It doesn't like flicker.
No, you don't want it to flicker. What you want it is to dim.
Yeah, it's
Mine,
just
mine is connected to this little guy. I don't know if the kind of light matters, but it's just this little tiny LED.
I know the one that Yejin had was a filament.
Yeah, does that make a difference?
Yes,
maybe?
because the amount of charge that goes through the filament is enormous. The amount of charge that you need to get an LED to light up and delight is actually quite small. I'm not sure.
I'm
Um,
wondering if it is actually like going down slower, just so quickly still that I can't tell the difference, you know?
Well, I know that the amount of power that you have for the new types of lights that are not filament lights are almost an order of magnitude smaller. Like if to get the same amount of lumens from a 100-watt filament light globe, if you were to use an LED light, the power consumption is much less, something like 12 watts or 24 watts or something. It's quite a bit smaller. If you relate that to the amount of charge that needs to be traveling through the system, it might be, look, the system that Yejin had was barely noticeable. I'm wondering if you change it by even just like by a quarter, could you even notice the difference in a quarter of a second?
I don't think so.
That's
So-
the problem.
It's because of the LED then, huh?
Maybe a filament light
Is there
might.
a way to
Hmm?
Is there a way to make it work with the LED without having to use anything else?
Make a bigger capacitor. Like, what was the surface area of your capacitor?
It was maybe, how big is this?
That big?
6 inches by 10 inches?
Okay, so that's 9 by 9. Let's make that a bit smaller and that a bit longer. So about that.
Yeah.
All right.
And then like, I used a smaller one. I used several different things. So try to make it even bigger.
There's oh goodness, that's a big B. The other thing
made mine this big.
that's pretty big. The other thing that you might find is that you could be having a another effect in a filament light globe. A filament light globe, you often see that resistance is related to temperature. So if you increase the temperature of a conductor, the resistance also increases. And I think resistance is an inverse to capacitance. So if I've increased the resistance through a filament light globe, it may take longer for the charge to actually make its way through. So you might be having a double effect there.
So your suggestion would be to make a bigger capacitor and try again?
Potentially. I mean, I don't know how you could, though, if you're limited to like A4 sheets of paper.
Yeah.
An A3 sheet of paper would be enormous. You double the amount of capacitance. But even doubling it, if you've doubling it, but you've got you've got to cover like 4 times as much. That's an enormous bit of
Do
paper
we
that
have
you
to
would need.
use what's it called? Aluminum?
No, any conductor works. But the property of the conductive material is basically it's got zero resistance. So if the conductive material has zero resistance, that's the only property that you really need. So aluminium is cheap and it's available.
Mr. Andrew,
Yes.
mine worked, but then like it's kind of hard to measure like the time.
Yep. Yours is probably only just barely noticeable. So you have a certain, your measurement is kind of tied to what is physically possible to notice with the human mind, with the human eye. So it's a very, very minute difference. But if you say it, you can perceive a difference.
So can I write? Yeah. So on like the report, can I just say what video?
On the report, can you just say what?
Or it's visible through your naked eye?
Yeah, it's barely not noticeable visually.
Yeah.
Why do I have no video of you guys?
Can I just say oh wait, but then you already like checked it, so
What do you mean?
whoa.
What happened?
I have no idea. I'm assuming that there was some sort of internet connectivity. I have reopened the other door, so maybe that'll let more Wi-Fi.
It looks like it's working, so it's on. Wait.
Let me just, I don't have a good visual here yet. All right, yep, it's on. Right. So you don't see a huge amount of difference. The capacitor doesn't seem to be doing anything.
That is the case.
Hmm. Interesting. How much power does that LED take?
Bruh, I have no idea.
I'm sure that LEDs would be taking a lot less power. Let me just have a look.
I don't have a non-LED light except for this, but this doesn't work.
The other light bulb is too big, I think.
Yeah.
Find something in between.
I don't have anything in between.
Do you have a normal incandescent bulb?
Oh, what?
A normal incandescent bulb.
Probably somewhere in the house.
I wonder if you can stick an incandescent bulb. I wonder if you can stick an incandescent bulb in a DC circuit. Because it really is just heating it up. Maybe you just need, maybe it requires a certain amount of power to be able to do it. Now these ones are stuck in an oscillating system. Alternating power supply. I'm not sure if you could actually get a reading on an incandescent bulb. If you could get a small incandescent bulb, like a 40-watt one or a 20-watt one, maybe. I don't get a lot of them around these days, though. Everything's gone LED or... Interesting. What about if you tried a motor?
I don't have a motor.
Not even for a toy car? The ones that run on run on DC batteries?
No idea.
I don't think so.
What else could you use?
I had the little speaker, but it was practically broken, so it didn't really help.
Yeah, that's the speaker needs some sort of oscillation to be able to get it to work and amplify. It might need AC current. I'm not sure. No, that can't be right because speakers work on a DC circuit. If you have a radio.
I have a different light, but it's like even smaller.
Show me.
It's like this tiny little red one.
Yep, that's an even smaller one.
Yeah, it's like super.
I wonder
I do wonder.
if you could add a resistor of some sort to the mix.
Can we make those?
I don't know.
Bonus points?
Make a resistor.
Plus a capacitor. Might as well make the battery and the light while we're at it.
There you go. I like the way you think.
Absolutely.
Okay. What you can do. You can make Franklin bells.
What's that?
Okay, a Franklin bell is a rather odd device. And the modern ones that people make are normally out of Coke cans. Here you go.
Out of what?
Coke cans. Like little cans.
Yeah, I heard something different.
Okay. Yeah. And then?
All right. So let me just share the screen. Okay. So what you have is you have this circuit. So this is so this is providing a very small amount of DC current. I mean, how do I do the annotation? No, I don't want one with a Van de Graaff generator. I want a Franklin Bell DC battery. You can charge it with a DC battery. I'm sure you can. Okay, here's a Franklin Bell with a DC battery. All right.
Does it work as a capacitor?
No. What happens? You'd be adding your capacitor into this system. So what happens is this. What would happen is this becomes negatively charged, which will, if you're running it that way, which will then cause this neutral charge thing to have positive ions come this side and negative ions on this side. And once it hits, the whole thing becomes negative. And this, because this is now neutral, this whole thing becomes negative. It'll then, which way will it swing now? It'll swing this way. And when it swings, this way, it'll then hit this side. And when it hits this side, what's going to happen? You're going to have the positive charge go there and it'll swing back. It swings back and forth. Now, the speed of that swinging has to do with the amount of current. Okay. I do want to get rid of that annotation.
So then, technically speaking, if we have a capacitor in there and we cut the power, then the bell thing will swing back and forth more than if we didn't?
It should go for a bit longer.
Okay.
Okay, so a Franklin bell is in a, okay, there we go. That's what should happen. Okay, I should stop share and I should start share again with the thing for the video. So what you should see, one with that's using a Wismer. Okay, so there's a few ways to make them, but you can.
Our homemade Franklin's bell uses a high voltage power supply instead. It can be a Van de Graaff generator, Wimshurst machine, normal kitchen implements, or one of many other devices. In the case of this Wimshurst machine, the charge is produced by the rotating discs and neutralizer bars. The electrons move to this collector, along this bar, and to the can. There they move from can to can via the tab. They then return to the disc via this other bar and collector.
Okay.
Note, Franklin's bell was actually invented in around 1742 by
How do I stop that sound? I want
this neat and novel use. So now
Okay, so you could do a Franklin bell. If you want to look that up, that could be a potential way to show the charge actually moving through the circuit. And if you disconnect the battery, there should still be charge in the capacitor to keep the tab moving backwards and forwards. Okay, we good?
I'm willing to try, but what if we make it that too, and then
And it
still
doesn't work.
doesn't work? Like, if we've made like 3 capacitors plus a Franklin bell, can't we like turn in and just like
Yes,
get
yes.
the same amount of credit for that?
There's a certain amount where you go, yeah, you've done some work.
Double light.
That's an interesting concept. If you were to add more power being used up at each point, you're increasing the resistance.
That's
So
true.
if you were to put the lights in series, like 5 or 10 lights or something, does that increase the power load? It should. Therefore, it should also allow you to see. Actually, it's already instantaneous how much when it dies. I'm not sure. I'm really not sure, Weston. I don't know. You might even want to be reducing the power. I really don't know.
Reduce. I have a small light.
A smaller light might work. Who knows? Anyway, I am going to go now because I have another class waiting in the wings. Are we all good with that?
Yes, sir.
All right. See you later.
Thank you.
Yeah, see ya.
Thank you.